So oftentimes we use the graphing calculator to help us solve equations by intersection, and this can be done in a few different ways, either looking for when two functions equal each other, when they have the same value, or when a function reaches a certain level, like say we want to know when a population reaches a certain number of individuals, or if we have just an equation that we can't solve algebraically, um, whether it be complicated on both sides of the equation or some expression equals a constant. We can do all that with the calculator. It works out to be exactly the same. So we'll see this through a few examples here. Pull these up. So the first example we'll walk through, I have two questions here, but they are basically equivalent. The first says find the points at which f of x, which is x squared plus x minus 2, and g of x, which equals negative 3x plus 4, intersect. So this word intersect means we're talking about graphing. And then the same question asked differently says when do f of x and g of x equal each other? So when they equal each other means they have the same y values or dependent values for the given independent or input values. So over here for my graphing tool, I come into y equals and I enter my two functions into the y1 and y2 slot that I want to see intersect. And again, there's no guarantee that two functions will intersect, so this is one way that we can check and see that it happens. So to start off, enter these functions in, and then you want to set your window. Now you can do this in a custom way if you know kind of where you're looking, or you can start by telling the calculator I want to look at the standard zoom, which is from negative 10 to 10 on both axes. So I say zoom 6. That usually gives us a good baseline before we start tinkering with the window. So here it draws my y1 first and then my y2. And I have a suspicion that they actually intersect not only here, but somewhere up here, just by the way that this curve is bending and this one is straight. So to see a little bit more of that action, we can open up the window in the y direction. So we'll open up the y max to, let's say, 25. And you might open it up a little bit at first, see it wasn't quite enough, or you might have opened it up too much, and then you can tinker with it after. The 25 should be sufficient here. We see, yeah, it turns out these things intersect here and here. With a little bit more analysis, you might know that this is a quadratic and this is a line. So we know this function isn't going to bend backwards somewhere else. So you might try zooming out a few times or just looking at what function family you're dealing with. But that's outside the scope of this video. So we're just talking about how do we find where these functions are equal or where they intersect. So for that, we use this button here, not the trace button, but the calculate button. So we use second trace to get to this calculate menu, and we're looking to calculate the intersection of the two curves. So hit enter here. It'll ask you, hey, what first curve are you talking about? We'll say, well, we're talking about this y1 curve that this tracer is on, so we'll say enter. The second curve, it will usually choose the right one, but just to be sure, yeah, y2 is negative 3x plus 4. Then it'll ask you, where do you want to guess that the first intersection is? So you just move the cursor roughly in the direction of where the intersection is. It doesn't have to be perfect here, because it will do an approximation and find, okay, your intersection is at the x value of 1.16 on the x-axis and 0.513 on the y-axis. It's about 1.2 and 0.5. But we know that this intersects twice, so to find that second intersection, we'll repeat the process. Again, first curve, we'll say is our y1, and on the 84 it shows you. y2 is our second curve, and then our guess, we're going to try to move up closer to the first intersection. And we see here this happens at when x is negative 5.12 or 16, and y is 19.5-ish. Okay, so based on this information, we have the x and y values. We can answer the questions like find where these functions intersect, find when these functions are equal, find the x values in which the heights are the same, etc. These are all the same question that can be approximated with the calculator. Okay, and so this is helpful for when you have two functions where it's not algebraically easy or feasible to solve for those values. So for our second example, we're looking to solve an equation. This is an exponential equation. Whether or not you've seen that before is not super important. What we just know is that this might be algebraically more work than we're willing to do to solve for 12. And in some cases, it might be impossible, but not with this particular expression. So to do this, we head back to our y equals, clear out what we had before. Remembering that we changed our window, so we'll change it when we come back. But so what we do is we set one side of the equation as our y1. So we'll say 3 times 1.2 all to the x. And then the second value that we're interested in it intersecting is the value of 12. So we say y equals 12. That's the height that we care about. So then we'll come back to zoom standard. You might say, why would we do that? Because we know that it's going to be, the 12 is going to be outside. So, in general, I want to build that good habit of resetting your window, but really we know here that we need to increase the y. So let's go ahead and put this at 15 so we can see our height of 12 that we're looking to achieve. So you can imagine this might be like a population question asking, when does this population function reach 12 individuals or 12,000 individuals, whatever the model is. And we see right here, this is when this function achieves this value. And so we can use, again, that intersection to find, this might be the time variable or whatever. First curve is this one, second curve is this one. Where are we looking? Roughly over here. Again, don't have to be too specific. And it'll show us at the x value of 7.6, our y value is 12, which is exactly what we wanted. Okay, so we can solve equations that are set up to some constant value. And same thing with question 2, functionally the same question. When will this expression on the left with a variable be equal to some value? And we look at it and say, this is kind of nasty algebraically. Why don't I try this with the calculator first? We'll say 3x to the 2.5 minus 4 times x plus 1. That's the left side, so we're saying that's the y1, and then y2 is my 14.67. So we will enter that here, 14.67. Set the window. Again, we know we want to include 14.67 this time, so we might bump this up to 18. And obviously adjust for whatever you need to do. We could even move the y min up because we know we don't really care about values down there right now. And then head to the graph and see what we get. So there's our y1, which is our curve. Here's the level with which we want to see it at. So if I open that back up, just so we can see the behavior of the function, that might be nice, but unnecessary. So here we see it starts at 0, shoots off, and then hits that level of 14.67 like we wanted. And so we can, again, use the intersect. Go find where that should be. Being a little fast here, because we've done this 4 times. This is the x value, which makes this equation true. That's what we're looking for here. Okay, so if you can't do the algebra, or you just kind of want a verification or a quick approximation to get started for a function like this, or an equation like this or like this, then this would be the way to go. Okay, in Desmos, let's take a look and see how this would work out. So it's a little bit more Web 2.0, as they say, to do it this way. So here I can actually type in my 2 functions that we care about. Minus, 2. And g of x was negative 3x plus 4. So here this has scrolling and pinch zoom functionality, or if you have a mouse with a wheel on it, the scroll wheel will zoom in and out, and that works the same way as setting the window. Or you can come up here to this wrench, and this allows you to set your x min, x max, y min, y max in the same way. And also increase the size of the font and stuff just to make it look a little bit nicer. That's all you really need to know for now. And then to find the points of intersection, it's as simple as clicking on those points where you see them. it will auto-populate these things. It will also round them to 3 decimal places, which may not be appropriate. So in certain cases like this, you might need to do a little bit more number crunching to get the more expanded value. And that could be as simple as scrolling in to get closer and closer to see what that value might be. Okay, so this is finding the intersection of 2 functions. And again, you can name them, which is somewhat nice. And then our second set of problems were what? The 3 times 1.2 to the x, and when this equals 12. When this equals 12. So here, just typing this in will actually give us the 0 that we want. However, we should write it in the same way, carry forth this practice that we set up. Y equals 12 and y equals 3 times 1.2 to the x. We'll see where they intersect. Again, it's 7.604. If you do need more degrees of accuracy, turns out it is not as simple as just zooming in. This used to be the case, and it's no longer. So from here, if you really need to get more detailed, even though this is just an approximation, you could turn this function into a table of values and try to dial it in a little bit closer this way. So we know this was at 7.603. And so from here, maybe generating some more values and getting closer and closer to see a more specific decimal point. But that's, again, kind of outstripping from where we need to be for this video. So our last question was this here, 3 times x to the 2.5 minus all this stuff equals 14.67. So again, this is the same question. 3x to the 2.5. That's one function, and the other function was 14.67. And again, let's just go ahead and reset our values here. Give us a bit of a baseline. Again, we want to see 14.67, so I'm going to scroll out till we see it. And then find that point of intersection, and here we go. X value, Y value of when they're equal. Okay? So again, this is how you would solve equations using the intersect method for both Desmos and the graphing calculator.